So let's finish talking about bonding. This is my textbook is chapter 9, all of chapter 9. Yours is just section 0.4 through 0.8. It covers the same material. There we go. So up to this point, we've been using the valence bond theory and localized electron model to describe the bonding of different simple molecules and their shapes. And those techniques still work. The problem is that even though they predict the correct shape for some molecules, the shape cannot be related to overlapping of orbitals, which is what the valence bond theory depends upon. When those orbitals overlap, they have to be in a certain geometry and angle and position to give you the molecule you expect. And for some molecules, this theory does not correctly predict those. For instance, methane, CH4. The shape of the molecule is predicted as tetrahedral because it has 4 groups around the central atom and no lone pairs. So that's the molecular geometry. And the bond angle should be 109.5 degrees. And that's exactly what we see. The problem is that the valence electron configuration for carbon, we know is, let's see, 6 electrons. So we have 1s2, 2s2, 2p6. These are the orbitals that would be involved in the bonding. The s orbitals are spherical. P orbitals are going to be like this, like that, and then another one into and out of the board. So you have 3 possibilities, X, Y, and Z. Right? So how do you bond hydrogen to these 2 and to these 2? Oops, sorry. I added a bunch of electrons. If you bond 2 hydrogens to this one, they could be anywhere around here. 2 hydrogens to this one, they have to be oriented a certain way, 90 degrees to each other, right? And that doesn't give us a symmetrical tetrahedral molecule. Right, so there's the S2P2 for the valence shell. Right, and because the orbitals are different shapes, we can't reconcile the valence bond theory with reality. So what we have to do is, based on the experimentally determined arrangement of hydrogen atoms in methane, we've got to come up with a different fix, right? Just like we did earlier with resonance. Right? We could draw 2, 3, 4, however many equivalent Lewis structures, but we couldn't decide which one was which because they were all essentially the same, except we had different positions for the, usually the double bonds move around. So we had to invent resonance to cover those bases. Well, now we're going to invent hybridization, and that was proposed by Linus Pauling in 1931. And what he said was, when the bonds form to make the molecule, and in our case, we're talking about methane as our example. When those bonds form, the bonds restructure themselves. They basically hybridize. They take some of the character from the s orbital and some of the character from the p orbital, and they create, we've got an s, we have 3 possibilities for the p, x, y, and z. They take those 3 and this 1, and they produce 4 equivalent sp3 hybrids. And these are spaced pointing at the apex, the different apexes of the tetrahedron. Now we can get orbital overlap with these individual hydrogens that explains the tetrahedral structure of the molecule. All right. So that solves methane. And I might add that we use Schrodinger's equations to solve the quantum, the nature of the atom. This quantum mechanical model for the atom works for molecules as long as they give us the right bond or orbital positions. So what we had to do is, or what Pauling had to do, was take those Schrodinger equations and modify them so that they would give him this hybridization and produce the geometric arrangement of a tetrahedron. So this isn't just a figment of his imagination. He may have dreamt it one night that this is the fix, but then he had to prove it mathematically, because quantum mechanics is all math. It's all probabilities. So the equations have to bear this out. And we're still working under the assumption that all the electrons belong to each of the atoms they came from. It's only with the overlap of orbitals and the sharing of those electrons that we get the bonding under this model. Right. So sp3 hybridization gives us a tetrahedral shape. Let me put that over here. Let's see, the hybrid is sp3 hybrid gives us, let's see, let's also add number of groups, electron groups. This would be 4 groups. It would require an sp3 hybridization to give us 4 groups. And the shape, well, geometry, I should be consistent. The molecular geometry, actually, molecular geometry depends on the lone pairs. So let's just say the electronic geometry. And the molecular geometry, in this case, is tetrahedron for both of them. So that's what we get with an sp3 hybridization. Now, when we look at the energy of the orbitals that are produced, we know that even though the principal quantum number is 2 in this case, and 2 refers to energy, that's an energy range. So the s orbitals are typically a little lower in energy than the p orbitals. And we talked about that penetration that gives them that average lower energy. So with the s a little lower than the p's, once you hybridize them, then you get something in between. And they have 25% s character and 75% p character. So that influences the energy to where the energy of the sp3 is much closer to the original p orbitals. That's all that's demonstrating. And it's not even semi-quantitative, it's qualitative. Because that's one thing that the localized electron model, the valence bond theory, cannot tell us. They cannot calculate energies. They're not built that way. So on the left, we've got the atomic orbitals that go into the hybridization, and what the mathematical equations, the wave functions, their solutions give us these shapes on the right. And each one has a nice big bulge pointing toward one of the apexes of the tetrahedron. Now, if this were an ammonia molecule, it'd be the same thing. except one of those would be occupied with a lone pair. Now, I think that's coming up. I'm stealing my own thunder. All right, so that's what it would look like with bonding with hydrogen and the overlap of their atomic orbitals. So with the ammonia molecule, we would write, you always have to start with the Lewis structure. So we know, actually you start with the formula for the compound. Right? That has to be proven. We have to know that it's real. Then we can waste our time on this other stuff. So that's real. So now we're going to take, let's see, nitrogen is 5. Yeah. 5, 3, that's 8 electrons, right? Okay. So then we go through the process. We would do this with any new molecule. 2, 4, 6. 2 electrons that go here. Okay. So we have 4 there. That means the electronic structure has to be tetrahedron. And that means this would be an sp3 hybrid. And 3 of those hybrids would be occupied in this overlap with the hydrogen. And the 4th one would have a lone pair. So it would kind of balloon out and push down on the others. So instead of 109.5, it's probably 107 degrees bond angles. Okay, write the Lewis structure, decide what the arrangement is, what the electron pair arrangement is, and use the VSEPR model to determine the geometry. And then from the once you know the geometry, then you can equate it to the hybridization that's required. There are more hybrids in here. We haven't got to all of them yet. Okay. So that's what it would look like. And we already talked about that. There's a lone pair at the top in an sp3 hybrid orbital. Oh, we're going to move on to a new one. Okay. So now we've got this molecule, ethylene. C2H4, is it? Yep, ethylene. Be 12 electrons? Is that right? 2 times 4 is 8 plus 4 is 12. Okay, so we have 2 carbons here. Then we have 4 hydrogens there. 2, 4, 6, 8, 10. Right? 2 electrons. Okay. So we have to work from the outside in. Hydrogen can't hold anymore. All right, so now we have to make an octet. So these 2 would go over here and make a double bond. All right. Now we can use the VSEPR model. Around each one of these carbons, they've got the same number of groups. So we've got 3 groups, and that's trigonal planar. Around each one. So we got trigonal planar in here for this one, trigonal planar. And it's going to be the same because we've got no lone pairs. Okay, so how do we hybridize this carbon to make it acceptable? We only need 3 to make a trigonal planar. So instead of hybridizing sp3, we hybridize sp2. Okay, and that takes care of 3 groups. Now, what happened to the other p? Well, it's unused until we make the double bond. And that's where the double bond comes from.
So you use the other one to make a double bond?
I'm sorry?
So you use the other one to make a double bond?
Yeah, you use that unused p orbital. We didn't use one of the p's in here.
Yeah.
And I think, let's see, the shape is trigonal planar, yep. Bond angles would be 120 degrees. And we don't use sp3 hybridization because we don't need 4 orbitals. We need 3. There we go. So we use two p orbitals. One of the p orbitals is unused, which is oriented perpendicular. It would be like into and out of the board. And we talked about sigma bonds and pi bonds. That's coming up. Sorry. We're going to talk about that in a minute then. Okay. In fact, right now. So any bond that is is between the atoms. In this case, we have carbon here, and you get overlap, those orbitals. This leads to a sigma bond, right? And it has to be on axis with the two atoms. You can only have one sigma bond between two atoms. But if you have these unused p orbitals and they overlap off axis, those become pi bonds. So sigma bonds are on axis, pi bonds are off axis. Now you can have, as long as you've got one sigma, you can add a pi to it. And you can actually add two pi bonds to it. Right? If you have another unused p orbital, say this one would be in the plane of the board. If you have another one that's perpendicular to the board, those can overlap too and give you another pi bond. So that leads to a triple bond. We don't need it for this one, but you can do it. Right. Now, when we look at the energy distribution, we find that with the SP, we have maybe 2/3 character of P and 1/3 character of S. So the energy now is lower for the hybridized orbitals. And that 2p is at the same energy level as the original 2p before it overlaps. So there's a representation of the sp2 hybrids in one plane, and then the unused p orbital in the perpendicular to that. And I think we've got yeah, that's what I just said. And this is what the solution to the wave equations will show you is the shape and the direction of those sp2 hybrids. Okay. So there's an artist's representation of this molecule. It's probably a little easier to see what's going on there. With the hydrogens in place, their orbitals, their s orbitals overlapping with the sp2 hybrids to give you the positions for the hydrogens, plus the 1 sigma for the carbons. And then the overlap of the unused p orbital gives you the pi bond. So you have a sigma here and a pi bond there. Now, this doesn't mean that we've got 2 bonds here. This means that there is overlap of this orbital on both this side and that side of the bond. And that's just talking about probabilities. That gives you a probability distribution for where we can find the electron. It doesn't say that we have 2 bonds there. We don't have 2 pi bonds. We have 1 pi bond. Okay. Carbon dioxide. Let's see what we do with that. All right, so we have 4 here, and 6 times 2 is 12, 16, right? Right? Oxygen, yeah. Yeah, oxygen 6, 2 6s is 12 plus 4 is 16. Okay, so we get a carbon here, and oxygen there, so that's minus 4 equals 12. 2, 4, 6, 8, 10, 12. And we did, I think in the past we've done the formal charge on this one with 2 double bonds versus a triple and a single, and found that the 2 double bonds is better. So we're going to make We're going to take those two and make a double bond. We're going to take these two and make a double bond. That is 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Everybody's got an octet. Okay, so now we know that this should be linear. This should be linear. And since there are no lone pairs around the carbon, then we've got two groups around the carbon, which means we only need one S and one P to be hybridized. And so we're going to have two SPs. This will give us 3 sp2s, and this will give 4 sp3s. In this case, we've got a sigma bond here, and we've got a pi bond also. So what that means is this carbon has unused p orbital here and an unused p orbital here to overlap with unused p orbitals on either side of these with these oxygens. So you get an overlap here, and let's see, let's keep them 6. That one right there, and then this one would overlap this one, that one, to give you the pi bond on that side. So the shape of the molecule is linear, and the bond angle has to be 180 degrees. Okay, so we only need one S and one P. That leaves the 2 unused p orbitals to serve for the pi bonding. Now the energy level for the sp hybrid drops even lower, because now we have a p character, 50% p and 50% s, and s is a lot lower than p, so that brings the bonding energy down, which actually means more stability. And that's what the wave equation solution makes it look like. Okay, so now we've got if you focus on the carbon, you find that those kind of greenish blue orbitals on the level plane are the sp hybrids, and the orange or goldish ones are the unused p orbitals. Now, oxygen also has to hybridize, right? Because around the oxygen, now we have 1, 2, 3. We have 3 groups around the oxygen, which means it's sp2 hybridized. So you can see those green, right? Trigonal planar, but only one of them is bonded, and the other 2 have the lone pairs in them right here and here. Okay. But it also has unused p orbitals. All right, it only has one set of p's on this side and one set of unused p's on that side to overlap. So carbon contributes 2 unused p orbitals, and each of the oxygens contribute 1 per on the unused p's, and that's where you get the overlap for the pi bonds. And this is all required. This hybridization is required because of the basic postulates of the valence bond theory and the localized electron model. Right? We're stuck. We have to do this. Otherwise, that model is finished. We can't use it anymore. So this is how we compensate. All right. Now we're going to go to dinitrogen, diatomic nitrogen gas. Yeah, okay. So we have N2, nitrogen has 5, yeah, so it has 10 electrons, have to be positioned. All right, that's -2, it's 8, 2, 4, 6, 8. All right. Now, 2, 4, 6. Is that right? That doesn't look right. Let me start over again. Dinitrogen.
That would be right. They would have to do 1,
1, 2, 3, 4, 5. Okay. So we'd have 10 electrons. Okay. We have a nitrogen with a And that uses up 2. There's 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8, right?
That's right, that's wrong.
Okay, 2, 4, 6. Oh. So if we move, I know what we're supposed to end up with.
Yeah. Yeah.
Okay, so if we move these 2 over into a bond,
And then move to the side.
that's 2, 4, 6. Yeah, then move these 2 over into another bond. Okay, now we're good. All right, 2, 4, 6, 8. Okay, we're good now. So this is the Lewis structure, and this would be linear. And each nitrogen has 2 groups around it, right? So each nitrogen has to be sp hybridized. That means it's got 2 unused p orbitals. Right? It's got 1 sigma here, it's got a pi here, and a pi here. Okay. So there we go.
So those 2 other piles, they're not extra bonds,
They're unused p orbitals. Oh, wait a minute. The extra pi's.
yeah, they're not extra bonds, they're
Yeah. Yeah, there's a triple bond there. Yeah. I think I got a picture coming up that'll help. But it's still, each nitrogen is still sp hybridized because it only needs 1, 2 on either side for this sigma and this lone pair. So that gives it 2 new hybridized orbitals, 1 position for this one and 1 for the bond on each side. And then we have the extra p orbitals. We have 2 unused p orbitals. And one of those p orbitals on this side overlaps with this one to give you one of the pi bonds. And then the other one into and out of the board overlaps to give you the other pi bond. All right. Okay, I already said that, said that. Okay. And then this is what it would look like. So you can see in the yellow, you've got the unused p orbitals, and the green are the hybridized sp orbitals that overlap first, and then you get the overlap of the unused p's to give you 2 sigma bonds, 2 pi bonds. Okay.
They complete, like, it's just complete.
I'm sorry.
Like, go back.
Yeah. Where do you want me to go?
Okay.
Okay.
That say D. Okay. That D shows the complete what it looks
Yeah. A, B, C, and D.
Yeah.
Yeah. The D shows the finished product. C it removes the sp hybrid orbitals to show you the overlap for the pi bonds. And then the D is complete. Yeah, the D puts everything together in one. Okay, let's do PCl5. All right, phosphorus is in the nitrogen group, so it has 5. 7 times 5, 35, that equals 40. So we know that we have P in the middle.
to be 30.
There. And if we put 6 more around each one of these chlorines, 6 times 5 is 30, right? 2, 4, 6, 8, 10, minus 10 for those. So that uses them all up. Yeah, we're done. Okay, now we have 5 groups. So how are we going to get, we've used up all of our S's and P's. How are we going to get 5 groups? Well, notice where phosphorus is. Phosphorus is in the 3rd period. We have access to d orbitals. So we take one of those d's. Now we have 3, 4, 5. Now we have 5 hybrid orbitals composed of 1 d, 1 s, and 3 p's. So dsp3, and we know that the shape is going to be what with 5 groups? They're going to what? Bipyramidal. Is that what you said?
No, I was going to say,
All right. So the shape of the molecule is trigonal bipyramidal. Well, there we go. Bond angles. The bond angles, I have to draw a picture for bond angles. There's a trigonal, phosphorus in the middle. We have one up here and one down here. Okay, so we can have a bond angle between here, say chlorine. The bond angle from here to here is 120 degrees. Okay. Bond angle from here to here is 180. The bond angle from here to here is a right angle. It's 90 degrees. So for this molecule, you've got all 3 of them. All right. So with these 5 equivalent orbitals, we need D2sp3 hybridization. Where is it? Oh, there it is. Right there at the top. DSP3, excuse me, DSP3. Okay. Is the chlorine hybridized? Yeah, because the chlorine has a 3s and 3 p's, so it's got to hybridize also. It's got 1, 2, 3, 4 groups around the chlorine, so it's got to be sp3 hybridized, and that's what it's showing there. A tetrahedral arrangement of the orbitals around each chlorine, and only one of them overlaps, and the other 3 have lone pairs in them. Okay, let's try another one. Xenon tetrafluoride. This one's 8. This one's 4 times 7 is 42. 50? No, wait a minute. 4 times 7 is 28. 28, 36, right? 36 electrons. Okay, xenon in the middle. Fluorine, 2, 4, 6, 8, which is equal to 28. So 4 times 6 is 24. We have 4 electrons left, 2 here and 2 there. Okay, what's the shape? Well, we have many groups? 1, 2, 3, 4, 5, 6. 6 groups means octahedral. Okay, so guess what? We need another d orbital. So we'll hybridize 2 d orbitals, an s and a p3. That gives us octahedral. Now the shape of the molecule, though, remember you have a square in the middle with a xenon here, and then we have, that gives us the octahedral shape. Where do the lone pairs go where the fluorines go? Well, for the octahedral group, the lone pairs would always go on the apex, and the fluorines go on the square. So we have a square planar molecule. Well, octahedral shape for the electronic shape, but a square planar for the actual molecular geometry. bond angles would only be 90 degrees. And that's D2sp3 hybridization. I don't know why they put the D first, because if they put them in order of energy, the S would come first, and then the P's, and then the D's. But for some reason, they always put the D's first. We know that the hybridization is not sp3. In other words, if we crossed out those like that, we said, okay, we've got 4 bonds to that xenon, then we might be fooled into thinking it's sp3. Well, if it's sp3, it would give us a certain shape that we could experimentally determine. But the determination tells us that the shape is square planar and not tetrahedral. Okay. So we already did that. Yeah, we already did that. And here's a table of everything that I put on the board. It's right there. So once you determine the geometry, the electronic geometry for the molecule, that tells you how many bonds or how many groups are around the central atom. Once you determine that, then you can go to the hybridization, because hybridization occurs in this order. If it's 2, it's sp. If it's 3, it's sp2. 4 is sp3. 5 is dsp3. And 6 is d2sp3. Right? It's that regular. Okay, let's take a little more difficult situation here. Maybe, maybe not. Hydrogen cyanide. Okay, got 1 there, 4 there, and 5 there, so that makes 10 electrons. Got carbon in the middle, nitrogen, hydrogen, 2, 4, 6 electrons. 1, 2, 3, 4, 5, 6. Work from the outside in. We used them all up. Okay, now how are we going to do this? We don't need anything on the hydrogen side, but we do need, this only has 2, 4. We need another one and another one. There, like that. So 2, 4, 6, 8, 10. We still have the same number of electrons. I didn't create any or destroy any. Around that carbon is linear, so it's sp hybridized for the carbon. How about the nitrogen? 1, 2, it's also sp hybridized. Okay. Now, the bonds, this middle one here is going to be a sigma, and each one of these is going to be a pi. You've always got to have 1 sigma before you can have any pi's. All right. So let's see, we got a drawing here. Yeah, we got a drawing. Of course, that one's a sigma between the hydrogen and the carbon. And then you've got another sigma here, and you got a pi there and a pi there. Okay. All right. Let's see. I think we've done some of these already. Ammonia, we know that one's going to be sp3 hybridized with 109.5 degree nominal bond angle. We know it's a little less than that. How about SO2? SO2, S and carbon and oxygen are both in the same group, so it's 6 and 12 is 18. We have S in the middle with oxygen on either side. -4 is 14. That's 12. So we have 2 left over that have to go on the sulfur. Okay, that's 3 around the sulfur, which means trigonal planar or sp2 hybridized. We have 4 around the oxygen, which means it's sp3 hybridized. Both of them. Let's see. Oh, and And since this is sp2, its trigonal planar means 120-degree bond angle. But it's going to be a bent molecule because if you cover up this lone pair, you get these oxygens down there like that, which makes it polar. I mean, that wasn't the question, but I'll throw it in for free. All right, krypton difluoride. Now we got 8 here, and 2 times 7 is 14. So we have 22 electrons. Krypton, fluorine, 2, 4 equals 18. 2, 4, 6, 8, 10, 12. That's 6, 2, 4, 6. So around that krypton, we've got 1, 2, 3, 4, 5. 5 groups. That's dsp3 hybridized and it's trigonal bipyramidal. But if we draw the structure and look for bond angles, right? Where do the lone pairs go? The lone pairs on trigonal bipyramidal go on the triangle. So the fluorine's here, the fluorine's there. This is a linear molecule, and the bond angles is 180 degrees. Okay, it's nonpolar. We know it has to be this way because this dipole moment cancels this dipole moment. If they were anywhere out here, then we would have a net dipole and we could measure it, but it's nonpolar. So we know that that's the only way it can happen. Okay, how about, we did carbon dioxide already. All right, 180 degrees, sp hybridized. And ICL5. Iodine pentachloride. Okay, that's 6 times 7 is 42 electrons. Okay, iodine's here. 1, 2, 3, 4, 5. Chlorine, 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 chlorine. 2, 4, 6, 8, 10 equals 32. So that's 6 times 5 is 30. We have 2 electrons, they go here. Okay, so this is 6 groups, means it's octahedral, D2sp3 hybridized around the iodine. Let's see. That would be, let's see, this, like this, like that, iodine in the middle. And we have something here and something here. The lone pairs are going to go up here. So the other chlorines are going to go here, 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 here. I should have drawn it the other way. If you pick it up, it's the actual geometric shape of the molecule is square pyramid, like the Egyptian pyramids. And the bond angles, 180 is gone because there's nothing up here. But we can have a 90 degree there and a 90 degree there. Only 90 degrees are bond angles for this molecule. D2sp3 hybridized. Okay, so this is just a summary of what we've been doing. And there's no mystery to that. This is a statement of the limitations of the localized electron model for the valence bond theory. And some of these things we discussed and some we didn't. First of all, it incorrectly assumes that the electrons are localized on the individual atoms, and they're only shared when there's a bond involved. And in order to get the Lewis structures to behave, if we have more than one, we have to invoke resonance. We didn't mention this one earlier. I don't remember if we had an example, but free radicals are difficult to deal with in this model. Remember what a free radical is? It's a molecule with an unpaired electron. Right? I'm trying to think of one. Is this one, 2, that's 5 and 12, 17 electron. Is that right? Yeah. So,
Yeah, that would be.
so that's -4 is 13.
Yeah, they'd have 6 and nitrogen.
Yeah. So that's a free radical as an unpaired electron. These guys are extremely reactive. And you probably heard in the popular broadcasting, you need to take our antioxidant, right? Super beets. It scavenges free radicals that damage your cells, which is true. I don't know if the product works, but free radicals are damage to the cells is attributed to many free radicals. Right? In younger cells, like in teeny tiny people, their free radical scavenging mechanisms are much more active. And that we would have in our bodies. Some forms of oxygen are usually, because there's lots of oxygen. I can't name any offhand. They usually result from chemical reactions, biochemical reactions in the body can produce free radicals.
So oxygen involved.
Well, not diatomic oxygen is not a problem because all the electrons are paired and they're bound together in diatomic form. But other forms of oxygen as a consequence of reactions can come out with unpaired electrons. I can't give you a good example right now. But types of molecules that will scavenge those free radicals are those with lots of double bonds in them. So the unsaturated fatty acids, like the omega-3s that are prevalent in fish oil, are effective scavengers of free radicals. That would take, I'd have to study on it for about a week or two. And then we'd have a whole lecture on nothing but free radicals. And if I were teaching biochemistry currently, then that would be a topic that we'd want to tackle. But I haven't taught it in a while, so I'm kind of rusty. Okay, so that's the second problem. The localized electron model does not deal well with free radicals. And I mentioned this one earlier. It doesn't give us direct calculated information about bond energies. That we have to determine those empirically. All right. There was one other. Let's see. It escapes me. I remembered it for my Beckley class, but I can't remember it now. This is where I normally would pause if we had a bi-weekly meeting. There wouldn't be enough time to cover the whole thing. So now we're gonna get into it again. I'll leave that up just in case we need a reference. Thus, the ultimate solution to these problems is a whole new model. Remember what I said about when a theory fails, we have 3 options. Right? You can modify it, which is what we've been doing, right? With resonance and with hybridization, we've been modifying the localized electron model to account for its shortcomings. Or you can throw it out, start over. Right? Or you can restrict its use. So that's what we're doing here. We're restricting the use of the localized electron model to things which it can answer questions. But ultimately, we need a new model that will give us more information and comport without a lot of modifications with reality. And that's the molecular orbital model. Right? It's essentially different than the localized electron model in that instead of assuming that all the electrons in the molecule belong to individual atoms and they're just shared in bonds, molecular orbital model says, all right, this is the molecular equivalence to communism, right? The molecule owns all the electrons, and they're shared over the entire molecule. So we need a new system that creates a new set of orbitals that are assigned to the entire molecule. So all the atomic orbitals are used to make this new set of molecular orbitals, and the atomic orbitals now are gone. And the molecule now has a set of molecular orbitals with which to populate with electrons. That's the gist of the difference between the two models. Now, just a reminder, we still call them orbitals, even though we don't subscribe to Niels Bohr's planetary model anymore. He called them orbitals because the electrons were viewed as little planets circling the nucleus, and they don't do that. But we still sort of got stuck with that name. So we call them orbitals even though they're not. And this molecular orbital model is also based on quantum mechanical equation solutions. We just have to modify the equations so that they give us what we want. And they also agree with reality. So here's a side-by-side comparison, right? Atomic orbitals for the localized electron model, and molecular orbital says, now we have molecular orbitals instead of atomic orbitals. Okay. In the localized electron model, we treat the individual atoms with the quantum mechanical equations, and those are extended then to the molecule. Whereas with the molecular orbital model, we take those quantum mechanical solutions and apply them to the entire molecule. I mentioned this one before. Electrons belong to atoms for the localized electron model, and they belong to the collective with the molecular orbital model. This is one thing that's the same for both. When we create these new orbitals, they still can only have 2 electrons each. They obey the opposite spin rule. You can only have 2 electrons for each orbital, whether it's molecular orbital or a localized electron model. And we solve these equations. On the localized electron model, we solve the wave functions for the atomic electron probabilities, and they're quantized energies, right? You can only move from here to here to here, nothing in between. And the same concept works for molecular orbitals also. They're a different set of equations, but they're still quantized. So your electrons can only occupy this orbital or this one or this one or this one, nothing in between. So there's consistency there. When we take all the atomic orbitals of all the atoms in a molecule and throw them in the blender, we get the same number of molecular orbitals pop out as atomic orbitals go in. We conserve the number of orbitals. They're different when they come out, but they're still the same number. Now, how do we do that? Well, let's say we had, let's take the simplest one possible, hydrogen. Right? If we have dihydrogen bonded together, we know it's got a single bond. Right? That hasn't changed. But let's go ahead and draw the molecular orbital energy diagram. So you got energy on this scale increasing from bottom to top. And over here, we've got this hydrogen and this hydrogen atoms. So these are the atomic, see, these are the atomic structures for each one. So this hydrogen is going to have a 1s orbital with one electron in it. And this one's going to have a 1s orbital with one electron in it. And when we combine those two, we have to have two orbitals come out of this. So the way the molecular orbital model works is it makes one here, and this will be a sigma derived from 1s orbitals. And this one, at a higher energy than either of these, is a sigma star derived from the 1s. This is called a bonding orbital. This is called an anti-bonding orbital. Okay? So we follow the Aufbau principles, which says electrons go into the next lowest energy. And we can have two in this orbital. So we bring both of these over here. Now the other one of them has one spin and one of them has to reverse its spin. And this orbital has no electrons, right? This is the very simplest example of a molecular orbital model for a molecule. I've got videos coming up. Do I have time? Yeah, I got time. Let's see. And of course, this one's going to be a sigma because the bond is on the axis between the two. Now, the solutions to the wave functions give us a certain shape for this one, which is essentially, right, electron density in here, in that sigma bond. Now, the anti-bonding orbital has an electron density that's positioned outside on either side. So that means it's opposed to bonding. It's anti-bonding, right? If the electrons in here, they tend to shield the positive charges from repelling each other. And if they're out here, those positive charges are able to repel. So the best place for your electrons is in here if you want to bond. All right.
Waves can overlap. When that happens, the highs and the lows can build upon each other. Or they can align in such a way that they balance each other out. When they build upon each other, this is called constructive interference. When they balance each other out, this is called destructive interference. Let's look at what happens step by step when two waves travel through each other. Here's a moment when two highs overlap. This results in a combined high that's much higher. This is constructive interference. Now, here's a moment where all the highs are perfectly overlapping all the lows. We see a cancellation of the wave amplitudes. This is a moment of destructive interference. If you took a snapshot photo, you might think that nothing is happening. Change that to a video, and you'd see otherwise. In the next moment, you've got a case where the two lows are now overlapping. This results in a combined low that's much lower. Once again, we have constructive interference. So, constructive and destructive interference never occur at the same time. Instead, they alternate, one after the other. And then the two waves continue on their merry way, having traveled right through each other, amazingly unaltered. Check this out. A wave can bounce off of a rigid structure. Let's add a second wave. Cool. Let's add a second wall and try to confine a single wave. Aha. What we've got here is called a standing wave. Notice that to have a standing wave, the dimensions have to be just right, typically some multiple of the wave's wavelength. A musical instrument, such as a guitar or a flute, is engineered just right to accommodate standing waves vibrating within the instrument, producing beautiful sounds. That's good energy.
Out in the ocean, like the waves are chopping, like and flatten out. Like have
You can have, this is characteristic of any type of wave, right? You get that interference. In this discussion, we're treating electrons with, as if they were waves, not particles. If we were talking about the photoelectric effect, then we talk about them as if they were particles. But in this case, we're talking about them as if they're waves. And the Schrodinger equations are solved as wave functions. So we're assuming the electrons are waves. The difference is that with waves, the example was two waves approaching each other and they did something and they went on their way, right? They're continuous waves, right? So you get any number of possible interferences as they go past. But with electrons, it's all or nothing. It's either the equations are solved for either constructive interference or destructive interference, one or the other, but nothing in between. This overlapping of waves is called superposition. And interference, we've seen that. I don't need to beat that horse anymore. Constructive and destructive are possibilities. They have to be one or the other in order for the energy to be quantized. Right? If they're continuous, then all bets are off. This is what the hydrogen atom would look like. The one on the top is a depiction of the anti-bonding orbitals. The one on the bottom is a depiction of the bonding orbitals. And in this case, the MO2 is this one in that picture. And this is MO1. Just so that we're on the same, talking the same language. The energies, of course, are lower for bonding and higher for the anti-bonding. And remember, always in chemistry, lower energy is more stable. Anytime you can get lower energy, you have a more stable situation, whether it's an individual atom or it's a bond, it's a molecule, whatever. Lower energy, it equates to stability. Right, so there's a drawing of our, just like I did here. Now, the solutions to these equations actually give us values for these energies. We can calculate energies for individual atoms. We've done that before. And then we can also determine energies for this bond, the anti-bonding, and for the bonding. Those can come out of the equations. So that's a step ahead of the valence bond theory. Let's see. Yeah, we're still, when we call these sigmas, they're still on axis. Right? The sigma bonding orbital is between the atoms. The sigma anti-bonding is still on axis, but it's on either side of the hydrogen. Right? So it still abides by the sigma description. Okay, so for instance, if we have difluorine with 18 electrons, if we were to write this in a shorthand way, right, we just string it out, then we would say this H2 has a molecular orbital configuration, just like we did atomic configuration, electronic configurations. This one would be a sigma derived from the 1s with 2 electrons in it. That would be the description. Now, if we had, well, the next example, this is the way it would look for fluorine, difluorine. And from left to right is increasing energy, just like the atomic electronic configurations. Right? When you draw this out, it takes a lot of time and a lot of paper, right? This is quicker. And you've got a bunch of examples in your review document that do just that. What you need, all you need to know is what's the energy order. And then you can fill in the electrons just like before. With the sigmas, of course, you can only have 2 electrons. But with the pi's, you can, it's like you can have a double bond or you can have another one to make a triple bond. So you can, for each of the pi's, you can have 2. And each one of those can have 2 electrons in it. So the pi, in this case, derived from 2p can have 4 electrons, and the pi derived from pi star derived from 2p's can have 4 electrons. I'll show you a more complicated one in a minute or two. Let's see. Now, typically, we're only interested in the valence electrons. So what you might see is once we get to a higher, like past helium, say lithium and beyond, then we might leave the 1s's down here and just not even show them. And we'll just show the valence orbitals. Now, one other thing we can do with this is we can do a calculation called bond order. And all you have to do to calculate the bond order is to count the number of bonding electrons and subtract the number of anti-bonding electrons and divide by 2. And if you do that for this particular molecule, you get 2 minus 0 is 2, divided by 2 is 1. Okay? So if it's a whole number, we're pretty safe in saying that this is a single bond. And if we did that for maybe dioxygen, O2, we'd come out with a 2 here instead, and that would be a double bond. Or with dinitrogen, we'd come out with a 3, and that'd be a triple bond. But the bond order doesn't have to be whole numbers. It can be, but it doesn't have to be. It can be fractions. And the bond order, the higher the bond order, the stronger the bond, and the shorter the bond. Okay, that's still true. If we equate it to a single, double, or triple bond, then we're finding that the stronger bond is the triple bond, and that's dinitrogen, which is shorter bond, and it's stronger. And there's the calculation for H2. Now, what would happen if we added an electron to this molecule and we said H2 minus? Where would it go? Well, that extra electron would have to go up here in the antibonding orbital. And the shorthand would then be this 1s star with a 1 there. Okay, so if we did the calculation then, it'd be 2 minus 1 is 1, divided by 2 would be 1/2. So we would have weakened the bond by adding an electron to it, making an H2 ion. We'll weaken it.
Today we're going to discuss molecular orbitals. But before we can get to molecular orbitals, we have to first consider atomic orbitals, something that hopefully we're all pretty familiar with. So let's start with hydrogen. Here I have 2 isolated hydrogen atoms. And we know that each isolated hydrogen atom should have 1 electron located in the 1s subshell when in its ground state. And of course, we know that these electrons don't move in perfect circles around the nucleus as I've depicted them here, but they do define a region of space defined by a sphere. But when two atomic orbitals combine to help form a chemical bond, something special happens. In the case of hydrogens, those two 1s subshells combine and form a region of space known as a sigma molecular orbital. And a sigma molecular orbital is a region of space where the electrons live generally in between the two hydrogen nuclei, screening the repulsive force that their positive charges have on one another. So they stabilize, keeping these two nuclei close together. This is a bonding molecular orbital. But there's one rule that we haven't yet considered, and that is that the number of atomic orbitals going into an MO system must be equal to the number of molecular orbitals that that MO system contains. So our molecular orbital system is not yet complete in this depiction. We have one more molecular orbital that forms. That new molecular orbital that forms is called a sigma star molecular orbital. And it looks quite different from the sigma MO, doesn't it? If there were electrons inside of this sigma star molecular orbital, they would spend most of their time outside of the two nuclei, not screening their positive charge repulsions, and therefore would actually make the system very, very unstable. So let's think about what that means in terms of how hydrogen atoms come together to form a bond. In order to fully understand the molecular orbitals of an H2 molecule, we have to plot them in terms of energy. So here in this depiction, I've shown the two atomic orbitals here as these lines in blue. That will be our non-bonding energy. Unless there's an energetic benefit to forming molecular orbitals, these two atoms aren't going to get together and do that. So bonding molecular orbitals will be lower in energy, and antibonding orbitals will be higher in energy than this purple line that I've drawn. So let's combine these two different atomic orbitals into molecular orbitals and see what happens. When this happens, we always get a combination that is sort of centric around that non-bonding energy. In this case, we formed two new molecular orbitals from our two atomic orbitals. One is the sigma, one is the sigma star. Next, we have to populate our new molecular orbital system with the electrons that we know the atoms are bringing to the party. In this case, one from each. When we do this, notice that those electrons go into a lower energy orbital overall, and this lowers the overall energy of the entire system. So this energetic benefit that comes from forming and populating molecular orbitals leads us to the prediction that hydrogen will form a bond to another hydrogen. But beyond that, we can actually calculate exactly how many bonds will form. We call this the bond order, and it's calculated quite simply, using the number of bonding electrons minus the number of antibonding electrons, divided, of course, by 2, because we know it takes 2 electrons to form a chemical bond. In our example here of hydrogen, we have 2 bonding electrons, and we have no antibonding electrons. Consequently, our equation tells us that we expect 2 hydrogen atoms to get together and form a chemical bond with an order of 1. In other words, a hydrogen molecule should have a single bond. And that is, in fact, exactly what we see. Now let's move on to the next element on the periodic table, helium. Now I've put molecular orbitals here in quotations because, as we're about to discover, there really is no such thing as a helium-2 molecule. But to prove it, we need to use our energy diagram and combine the 2 atomic orbitals of helium atoms to find out what the energetics of bonding would be if it were to happen. So let's go ahead and do that now. We combine them into a system with a sigma and sigma star molecular orbital, and then we populate that system. Now, in this case, I have 2 electrons that can fill the sigma bonding molecular orbital, lowering the overall energy. But I still have 2 more electrons that have to go into this new molecular orbital system. And they have no choice but to go up in energy and populate the sigma star. The consequence of this is that there's no real energetic benefit to bonding. So two helium atoms have no real incentive to get together and form an He2 molecule. And in fact, that's exactly what we see. When we calculate the bond order, we find that 2 bonding electrons and 2 antibonding electrons leads to a situation where we predict a bond order of 0. In other words, we don't predict a bond at all. And when we study helium in the laboratory, that's exactly what we find. Helium exists as isolated atoms. Now let's expand our discussion and consider the molecular orbitals of elements from the second row of the periodic table. We're going to begin with fluorine. Now, fluorine, we know, has available p orbitals because it's in the second row of the periodic table. So atoms of fluorine have 3 different 2p orbitals to donate to forming new chemical bonds. And within those orbitals, we know each has 5 electrons. So let's think about, first, how those atomic orbitals combine, and second, how those electrons can populate the new system energetically to make something that's beneficial. When we combine p orbitals, we find that we have a system that looks a bit different, don't we? In this case, a grand total of 6 atomic orbitals must combine to form a grand total of 6 molecular orbitals. Now, the lowest and highest in energy of these correspond to the in-phase and out-of-phase overlap directly along the nuclear axis. Those we would call the sigma and sigma star molecular orbitals. But we have some new players here. Those are the orbitals that result from the side-to-side overlap of p orbitals that we call pi and pi star MOs. So we have to figure out exactly where the electrons will go in this system and whether or not there's a real energetic benefit to putting them there, and that will help us determine whether or not fluorine will make a bond. Let's do that now. When we put all of our bonding electrons in, we notice that 6 total electrons go into bonding molecular orbitals. This is a tremendous energetic benefit. The sigma and the pi bonding MOs are completely filled. But fluorine has extra electrons, and they have to go somewhere. And the next best available option is to place them into the pi star molecular orbitals. These are antibonding, so the energy comes back up somewhat. However, notice that overall, we still have a system in which, on average, our electrons are in lower energy locations when they're in the molecular orbital system. There's a little bit of an energetic benefit here. And our calculation for bond order lets us know that when you have a grand total of 6 bonding electrons and a total of 4 antibonding electrons, you would expect that species to form a single bond. And in fact, when we study fluorine in the laboratory, that's exactly what we find. A molecule with a single bond. Now let's move on to something a little bit more complicated. Here's another second row element, nitrogen. Nitrogen also has 2p atomic orbitals available, but in this case only 3 electrons in each. So let's combine those and form a new molecular orbital system. Now you might notice something changed here, right? Notice that the sigma molecular orbital is actually higher in energy than the pi. And this is an interesting phenomenon. It's caused by something called sigma-pi mixing. And we won't go into great detail into it here, but I wanted to point it out because this is how you'll probably see it in your textbooks. Nonetheless, when we use the electrons from nitrogen's 2p orbitals to populate this new MO system, notice that they all go into bonding MOs. And better than that, there's nothing left. There are no extra electrons to fill in those antibonding MOs and counterbalance the energetic benefits. So this is a tremendously energetically beneficial arrangement. When we calculate the bond order of an N2 molecule, we find that having 6 bonding electrons and absolutely no antibonding electrons, we expect a nitrogen molecule to have a triple bond. This is a very strong bond, which makes nitrogen gas almost completely inert. And again, when we go into the lab and study nitrogen, that's exactly what we see. A diatomic molecule with a triple bond. Now let's consider one more element from the second row of the periodic table. This time we'll consider oxygen. And I promise, I'm not wasting your time here. We're going to see something new. Now, just like any other second row element, oxygens have available 2p subshells. And we know from their electron configurations that each oxygen contains 4 electrons in those 2p subshells. So let's combine them to form some molecular orbitals. When we do this, we don't see any real surprises here. Sigma, sigma star, pi, and pi star molecular orbitals form. 6 atomic orbitals in, 6 molecular orbitals out. And if we fill them from the lowest energy to the highest, we notice that 6 of these electrons will go into bonding molecular orbitals, giving us a nice energetic benefit. But there are still 2 remaining electrons. And here's our new question. They clearly should go to the pi star MO, but should both electrons go into one, or should they each take a separate molecular orbital for themselves? The answer to the question is rooted in Hund's rule and the Pauli exclusion principle. Electrons will try to spread out and maximize spin. So, when they populate this new molecular orbital, they do so like this, raising the overall energy a little bit, right? Not enough to completely counteract all of those bonding electrons, so there will be a bond formed here. O2 molecules do exist. But even more importantly than that possibly is this. Notice that there are unpaired electrons in this molecule. And that means that our new oxygen molecule is paramagnetic. Liquid oxygen can be trapped within the confines of a powerful magnet. You may have seen this demonstration done before. And of course, just as before, our prediction is correct. If we calculate the total bond order of oxygen using 6 bonding electrons and 2 antibonding electrons, we find that the 6 and the 2 leads us to a calculated bond order of 2. Oxygen exists as a diatomic molecule with a double bond. So I hope that by now you're beginning to appreciate the power of molecular orbital theory. It not only confirms so many of the other topics we've already discussed on bonding, but it allows us to explain completely new properties that all of our other theories couldn't, things like the paramagnetism of oxygen. This is just the beginning of molecular orbital theory. You may want to consider in the future things like molecules that consist of 2 atoms that are not the same, or molecules that consist of even more than 2 atoms. There's much, much more to explore. But for this lecture, we're done. Thanks for watching, everyone.
Okay. So in this discussion, there were introduced 2 concepts that we're going to cover in a minute. But what we'd normally expect for 2s and 2p coming together in a homonuclear diatomic molecule. That is, homonuclear means they're the same element, but there are only 2 of them. You would expect this order, right? The 2 s's would give you a sigma and a sigma star, and then the 3 p's here would give you 6 orbitals here, but the lowest one would be sigma from the 2 p's, and the next would be the pi's from the 2 p's. Then the pi stars, followed by the sigma star. That's true for oxygen and fluorine. But when we move left from there to nitrogen and over, we get these energies are so close to one another that they flip. And the sigma 2p is on top and the pi's are underneath. That's sp mixing, or sigma pi mixing. So this would be good for oxygen and fluorine. Dioxygen and difluorine would work for that arrangement, and their abbreviated molecular orbital configuration would look like this. We just have to fill in the electrons. And I left out the 1s's also. So the 1s's would be down here. Let's see, would be sigma 1s, s, and sigma star 1s to cover all the electrons available. Okay. The homonuclear diatomic molecules are the easiest ones to draw and understand because they start out at the same level and it's all symmetrical. Now, the other concept that was introduced was paramagnetism. Paramagnetism is characteristic of any element that is drawn into a magnetic field, a strong magnetic field. Whereas diamagnetism is the phenomenon that you see with an element that, or a molecular construct that is repelled from a magnetic field. And if you've got all of your electrons are paired up, there are no unpaired electrons in this molecular orbital arrangement, then you get diamagnetism. But if you've got any that have unpaired electrons, which could be one, but it's usually two unpaired electrons, all you need is one, and you have a paramagnetic situation. Para means alongside, so it likes the magnetic field. It's drawn into it. Dia means opposed, so it's repelled from it. And this, we can actually measure paramagnetism or diamagnetism. If it's paramagnetism, it's going to be drawn into that magnetic field. So our sample goes in, and as it approaches that strong magnetic field down below, the electromagnet is calibrated so we know exactly the strength of the field. Then as it descends in there, you see the balance is going to exert a pull, and you can measure that pull. I assume if you put something in there that was diamagnetic, then as you got to it, it would go the other direction. Here's a really, really strong horseshoe magnet, and we pour liquid oxygen into it because gaseous oxygen don't behave. So when you pour liquid oxygen into that gap, it stays right there in the magnetic field until thermodynamics takes over and it evaporates. Oh, Professor Dave wants to talk. We got time? We got time.
It's Professor Dave. Let's revisit molecular orbital theory.
He knows a lot about the science stuff. Professor Dave explains.
We've learned a bit about molecular orbital theory and the ways in which it differs from valence bond theory. But let's expand on this knowledge now so that we can understand a phenomenon called sp mixing. But before we get into that, let's take some time to review the basics. First, let's compare valence bond theory and molecular orbital theory. Valence bond theory considers covalent bonds as being localized between a pair of atoms, resulting from the overlap of atomic orbitals or hybrid atomic orbitals. This overlap results in sigma or pi bonds, and we can use this theory to predict molecular shape. However, there are simple molecules that do not conform to this theory, like the diatomic oxygen molecule. Given this Lewis structure, where each oxygen atom has a full octet, we would expect oxygen to be diamagnetic and weakly repel a magnetic field. However, it does in fact exhibit paramagnetism, as liquid oxygen is attracted to a magnetic field. To explain this, we have to turn to molecular orbital theory, which differs from valence bond theory in that electrons are considered delocalized throughout the molecule, and atomic orbitals combine to form molecular orbitals, which are also delocalized throughout the molecule. These can be sigma and pi bonding orbitals, or sigma star and pi star anti-bonding orbitals. This theory ends up being better equipped to predict the arrangement of electrons in a molecule in certain situations. This is due to a process called the linear combination of atomic orbitals. In the modern physics course, we talked a little bit about the wave function, and molecular orbitals are combinations of atomic orbital wave functions. Just the way the wave function describes the behavior of an electron within an atom, molecular orbitals describe the behavior of an electron within a molecule. And just like atomic orbitals, they are filled when they contain two electrons of opposite spin. This theory requires that we strongly consider the wave nature of the electron. In the classical physics series, we talked a lot about waves and interference patterns. So to get the full picture of wave behavior in order to better understand molecular orbitals, check out this tutorial now. Otherwise, we simply need to understand that when two atomic orbital wave functions are combined, like these two s orbitals, there can be constructive interference, where the peaks line up with the other peaks. This causes the amplitude to increase, which results in a bonding molecular orbital, like the sigma s orbital. Most of the electron density is between the nuclei, which strengthens the bond. There can also be destructive interference, where the peaks line up with troughs. This causes the amplitude to drop to zero, resulting in an anti-bonding orbital, like this sigma s star orbital. Here, there is a node between the nuclei, which weakens the bond. The bonding orbital is of lower energy and will thus be filled before the anti-bonding orbital. For this to make more sense, we simply need to understand that these images of waves are just two-dimensional analogies to help us visualize the type of overlap. Electrons are three-dimensional objects, so the waves are in 3 dimensions, and constructive interference thus results in regions of greater electron density, while destructive interference results in regions of no electron density, which are depicted by these bonding and anti-bonding orbitals. We can do the same thing with p orbitals, utilizing direct overlap, which will yield sigma px and sigma px star molecular orbitals, or lateral overlap, yielding pi and pi star molecular orbitals from the overlap of py and pz atomic orbitals. Orbital number is always conserved, which is why the linear combination of two atomic orbitals will always result in two molecular orbitals, one bonding and the other antibonding. We can depict these linear combinations with molecular orbital diagrams, as we have seen. The dashed lines show how the atomic orbitals on the sides combine to form the molecular orbitals in the middle, such as we see here for hydrogen, with two 1s orbitals combining to form one sigma s orbital and one sigma s star orbital. If we go up to the electrons in the n equals 2 shell, we can see the 2s orbitals combining in precisely the same way, and then the 2p orbitals combining as follows, with the sigma bonding orbital and then pi bonding orbitals, followed by the corresponding anti-bonding orbitals. The good news is that these orbitals are still filled according to the Aufbau principle and Hund's rule, like we already know. This means that we fill them from lower energy to higher, according to Aufbau, and we will put one electron in each orbital for a set of degenerate orbitals before doubling them up, according to Hund. We've already learned in a previous tutorial how to fill in these MO diagrams for certain diatomic molecules, like O2, and how to use them to calculate bond order. Here's that diagram one more time, along with the calculation for bond order, with 10 bonding electrons, including the sigma 1s bonding electrons, and 6 anti-bonding electrons, including the sigma 1s star anti-bonding electrons. 10 minus 6 is 4, and 4 over 2 is 2. This explains the double bond in diatomic oxygen. But we also get an explanation for the paramagnetism of the oxygen molecule. We have 2 unpaired electrons in these antibonding orbitals, which does predict paramagnetism for this molecule. This is an example of the success of molecular orbital theory, as no other theory can account for this behavior. Now that we are up to speed, let's go over one other thing. The molecular orbitals that result from the combination of the 2p orbitals exhibit this order in O2, but this will change for other homonuclear diatomic molecules. Let's look at this diagram, which depicts the relevant orbital energies for all the potential homonuclear diatomic molecules in the second period, from lithium to neon. As we go to the right in the period, effective nuclear charge increases, so the atomic radii contract, and the orbitals get lower in energy. On the left, the pi 2p bonding orbitals are lower in energy than the sigma 2p bonding orbital, but on the right, the sigma 2p bonding orbital dips below and thus will be filled first. This discrepancy is due to a phenomenon called sp mixing, which influences the energies of these molecular orbitals. This happens when the sigma s and sigma p wave functions combine in such a way that the sigma s orbital becomes more stable and the sigma p orbital becomes less stable. As a result, we see the sigma s and sigma s star orbitals going lower in energy and the sigma p and sigma p star going up in energy. So much so that the sigma p orbital now sits above the pi p orbitals. Molecules like O2 and F2 have negligible sp mixing because the 2p orbitals in those atoms have some paired electrons. This raises the energy of the 2p orbitals, making them too dissimilar to the energy of the 2s orbital to allow mixing to occur. But going to the left on the period, where p orbitals have unpaired electrons or are vacant, the 2p and 2s orbitals are of similar enough energies that sp mixing will be prevalent and the order of the molecular orbitals will switch. While this is an interesting phenomenon, if we are only using these diagrams to calculate bond order, it won't matter because it is just the order of bonding orbitals that is being rearranged, so it won't affect a bond order calculation. Nevertheless, we have hopefully reached a more sophisticated understanding of molecular orbitals. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Okay, so I laid down these abbreviated forms for the no SP mixing and the SP mixing, and the only thing that switches are these two P's. Right, the 2p sigma switches for no SP mixing. Sigma is lower in energy than the pi, and for mixing, pi is lower than energy than the sigma. That's what that thing tries to show. Now this next one adds a little extra information to it. It also populates the molecular orbitals and shows which ones are paramagnetic and which ones are diamagnetic. And it also includes a bond order calculation and the observed bond energies and bond lengths. So we see that the molecular orbital model falls into line with good agreement with all of these measurable quantities. All right. So the molecular orbital model works for any size molecule, right? Not just homonuclear diatomics, but heteronuclear diatomics, and for multinuclear molecules. But that's a little beyond us here, right? I just want to show this example where we have carbon and oxygen together. And if we look at the atomic orbital energies, we find that oxygen is a lower energy than carbon for its S and P orbitals. And that's primarily because oxygen has a higher effective nuclear charge, right? And the orbitals are drawn in closer, which means lower energy. So we start off with carbon at its energy level and oxygen at its energy level. And for example, if we form a sigma bonding orbital from the 2s from oxygen and the 2s from carbon, in fact, the first sigma orbital is going to be lower, just a little bit lower than the oxygen. And then the sigma from the p orbitals is even lower still. So there is quite an advantage. If you can populate those bonding orbitals with electrons, there's quite an energy advantage to doing that. And in fact, this carbon monoxide, I think it has a triple bond. And it has 2, 4, 6, 8, 10 electrons. So 2, 4, 6, 8, 10. Right? Is a reasonably stable molecule. Now it's a nasty molecule, right? Because it's if you get it in your system, it latches on to the iron and hemoglobin and won't let loose. Right? So iron is what transports oxygen to your cells, the iron and hemoglobin. So the dioxygen bonds more weakly with the iron, and it's able to release when it gets to the cells where it's needed. But carbon monoxide, if it latches on to the iron in your hemoglobin, it won't let go, and it blocks out the oxygen from attaching. So when you experience carbon monoxide poisoning, you're actually being suffocated on a molecular level. Yeah, that carbon monoxide won't turn loose.
How do they treat that?
Well, that's a good question. If they catch you in time before any significant damage has been done, then they can flood your system with oxygen, and the equilibrium then favors the release. Now, carbon monoxide, I say it won't let go. It will let go under certain circumstances. If you it's in equilibrium with carbon monoxide or other gases in the air. So if you flood your system with oxygen, then the oxygen will gradually displace the carbon monoxide. It takes a lot of time, but it can be done if they catch you in time. They can put you in a hyperbaric chamber and increase the oxygen concentration to really high levels. And that'll flush your system of carbon monoxide.
But you get too much oxygen, like in your cells, like take on too much oxygen, like where
Theoretically, yeah. Yeah, you can have too much oxygen. But if you look at scuba divers, right there, the problem scuba divers have is not with oxygen, but with nitrogen. Right? Nitrogen in compressed air. So if you're going really deep where the pressure is huge, then you substitute a different gas for nitrogen. That's why they put helium in there. So helium-oxygen mixtures are for deep divers, because helium, it's characteristic of nitrogen that it readily dissolves in your tissues. So when you come back up and the pressure decreases, it comes out of solution really explosively. And that gives you a condition called bends. Can be fatal. But helium is less soluble in your tissues than nitrogen is. So, and in fact, oxygen is less soluble than nitrogen. Nitrogen is very soluble in your tissues. So when you come back up, you can equalize the oxygen and helium much more efficiently as you rise. And it doesn't create the problem that nitrogen does. So I'm not sure what depth they recommend to switch. Probably, and it depends on how long you're down too. Like if you go down with oxygen, nitrogen, you go down deep and you only stay there for a couple of minutes and you start coming back up, it's not a big a problem. But if you stay down there for the maximum allowed time for your tanks, then you have to come back up in stages.
Do, they mix that for roots of life? They're like a the oxygen in the tanks.
Well, yeah, right. It depends on the depth you're going and how long you're going to be there. If you go really deep, then you can hear recordings of people at depth talking, and their voices are way up here because of the helium. Right? Sound waves travel faster in helium than they do in air, so that increased speed increases the frequency of your voice, and your vocal cords vibrate faster. So that gives you that chipmunk sound. Okay, here's a heteronuclear diatomic molecule, HF. Hydrogen only has the 1s orbital, whereas fluorine has 1s, 2s, and 2p orbitals that are combined in the molecular orbital system. Here we're concentrating on the 2p and the 1s because those are the highest energy orbitals. And what you get is a sigma molecular orbital that's lower than the 2p of the fluorine and a sigma star that's higher than the 1s of the hydrogen. And we're only interested in the highest level electrons, right? So you can get this electron from 1s hydrogen and electron from 2p fluorine, and they fill this orbital, and that gives you a single bond if you calculate the bond order. Okay. Now, even with the molecular orbital model, you still get uneven distribution of electron density. So the electronegativity modifier still works. The electron density is going to shift toward fluorine because it is more, the density is going to shift toward fluorine because it's more electronegative. And it gives you a polar molecule. I mean, even with the molecular orbital model, you can still you get that electron density distribution is lopsided. All right. Now we're going to sort of combine models. And just remember that what I said was earlier, if you can lower the energy of the electrons in a bonding situation, you can get more stability. So you can do that by either lowering the energy of the molecular orbitals, or you can delocalize the electrons in the molecule. And that's what we're going to do here. What you can do, or what happens, is that if the conditions are just right, you can get a pi bonding system that is not just single pi bonds between different atoms, but you can get a pi bonding, a delocalized pi bonding system in a molecule. Perfect example of that is benzene. If we draw the VSEPR version of benzene, we get something like this, a hexagonal shape. Each one of these in organic chemistry where these lines meet is a carbon. It's just easier to draw it that way. And then it also has one hydrogen for each one. Then we'll have a double bond, and a double bond. Now, this can resonate under the old system with this one where we just move the double bonds around one position, right? And those can resonate back and forth under the localized electron model. But we know that's not the way it happens because we can measure the length of these bonds and they're all the same length. So we know there's not a double here and a single there. What we have is a pi system. And sometimes we even draw the molecule like this. And we don't draw the hydrogens either. If there's supposed to be with carbon, you can have 4 bonds. Right? So if you got 1, 2, 3 here, and you don't have anything else here, it's assumed there's a hydrogen attached to it. Right? Those are conventions in organic chemistry that you may or may not be introduced to later. Depends on your career choice. But this circle implies that we have a pi bond, a pi delocalized pi electron system. And I think that we've got a picture here that helps. Okay, there's the resonating situation. And each carbon is going to be, right, 1, 2, 3. It's going to be sp2 hybridized under this system, which leaves an unused p orbital for each one. So what we actually get is these overlaps of these p orbitals extend all the way around the molecule. That delocalization of electron density stabilizes the molecule. In fact, the benzene ring is extremely stable. When I studied in agronomy, we studied the decomposition in a natural environment, decomposition of, say, a tree. And when a tree falls, the first things that go are the simple sugars. Right? They're really easy to metabolize. Microorganisms go in there and just chew them up. The last things to go are the phenolic compounds, those with these benzene rings in them. It takes a very special microorganism with a special enzyme system to break those things down because they are so stable.
What part of the
It's in the wood. Yeah. The mass of the tree is composed of 2 things: cellulose, which is reasonably stable also, but there are more microorganisms that can break that one down. Sap. No, that's a movement of dissolved aqueous solutions. That's got simple sugars in it usually. But there are other, the wood is composed of a ratio of 2 types of compounds. One is the celluloses and the other is the lignins. The lignins are very complex polymers, but they do have these phenolic compounds, these benzene rings embedded in them, and they're difficult to break down. The way the paper companies do it is they use concentrated sulfuric acid, and they extract the lignins out of the cellulose and get the cellulose over here so they can make fine paper products with it. The lignins used to be a waste product, but now they found uses for them. These sulfated lignins are valuable for other reasons. And that's why when you go by a paper processing plant like is east of Lewisburg, they've got one over there. You can drive along the freeway and you can smell the sulfur. Well, you can smell the sulfur off-road too when you get close to one of the springs. Like the white sulfur spring, the green sulfur spring, they emit sulfur compounds, but the paper processing plant is really noxious.
They use sulfuric acid.
Yeah. And of course, if you ask them what that smells like, and they say, "Oh, that smells like money," because they're making paper and getting money for it. Okay, so this is a representation of that pi system, that delocalized pi system, which occurs. This is just a representation of the potential electron density. Where can we find these pi electrons? We can find them above and below in this ring structure, and that's why we draw that circle there to show 2 things. All the bonds are equal, plus we've got a delocalized pi system. We can also draw this for other molecules, like this nitrate ion. If we draw it with the resonance approach, we have to do these individual structures. Or I think I drew this one once for you also. We can draw those sort of partial bonds, partial double bonds, which represents equality. But in fact, what you have is a delocalized pi system, similar to the benzene. And that makes the molecule very stable. All right, this last slide is in there primarily for one reason. I mentioned earlier that we can use the molecular orbital model to calculate energies for molecules. So when we calculate these energies for the different energy levels, these different molecular orbitals where we insert electrons, we'd like to know whether or not those agree with reality. And this is one method to obtain the energies of those molecular orbital levels. So we take the molecule and we shine high energy photons at it. And I'll just make this quick. The energy of the photon, of course, is calculated as h nu, right? Planck's constant times frequency. That's the total amount of energy of that photon. When it strikes the outer electrons, then it delivers some of that energy to move them from their orbital energy level. All right, there's a nucleus, this electron, that energy level out to infinity. Certain amount of energy is required. Right? If there's any extra energy left over, then that's translated into kinetic energy. So this is the total energy, and we have the energy required to move this to infinity plus the extra kinetic energy. And you can measure that kinetic energy. So if you take the energy of the photon and you subtract the energy, the kinetic energy that it has once it leaves the atom, then you can tell what's the energy of the level it came from. So that's the energy, the molecular orbital energy. And you,
would you have other levels too?
yes, right. These come off. This one will come off first, and then you get another one. And I draw this as an atom, but it's part of a it's part of a molecule. And in fact, these orbitals are for the whole molecule. So this one comes off, and then the next one comes off, and it takes more of that energy to get it out. So the kinetic energy is going to be lower, and you subtract it from the photon energy, and you get the energy of the next molecular orbital. And yeah, it will decrease. As you get lower in energy, it takes more of that photon energy to get it out. So the kinetic energy would be lower. And once you calculate all those energies, they correspond exactly with the calculated energies for these molecular orbitals. These measured energies from the photoelectric spectroscopy are exactly equal to the calculated energies from the molecular orbital model. So that's nice. Okay, we're done.